Hello everyone, welcome back to the second video on Laplace Transform. Another forcing function is impulse function, which is denoted by delta t. The definition of impulse function or delta t is like that: delta t equal to infinity at t equal to 0 and delta t equal to 0 when t not equal to 0. That means the magnitude of an impulse function is equal to infinity and it exists only at t equal to 0. The concept of delta t can be found from this pulse function. Suppose ft be a pulse function with pulse with delta t and its amplitude is suppose a, and the area of the pulse is given by a times of delta t. Let us choose the pulse function in such a way so that the area becomes unity. Now if delta t reduces, amplitude increases since they are inversely proportional to each other. The impulse function delta t can be obtained from this pulse function of unit area taking limit of pulse width tending to 0 ft. As pulse width delta t tends to 0, we can say amplitude of this pulse tends to infinite. Another property of delta t is integration minus infinity to plus infinity delta t dt equal to 1. That means area under the impulse, its pulse width is 0 but magnitude is infinite, but the area remains unity. Similarly, for time shifted impulse function, you can write down delta t minus capital T, which is equal to unity at t equal to capital T only, otherwise it is 0. Now let us calculate the Laplace transform of impulse and shifted impulse function. So L of delta t, from the definition we can find integration 0 to infinity e to the power minus s times t multiplied by delta t dt. Now when delta t is multiplied by any function xt, the multiplication is possible only at t equal to 0 because delta t exists only at t equal to 0. This relation is equal to x0 times of delta t. We can write down e to the power 0, which is unity, into delta t dt. E to the power 0 is 1 and also integration delta t dt, that is the area of the impulse function, which is also equal to unity. So Laplace transform of impulse is unity. Similarly, for time shifted impulse function, we have integration 0 to infinity e to the power minus st to delta t minus t dt. Here also the delta t minus t multiplied by any function xt, this will be x of t, because delta t minus t, this shifted impulse function, exists only at t equal to capital T here. Only at that point xt is being multiplied with delta t. Otherwise delta t minus capital T is 0 always. So the multiplication gives us x of t multiplied by delta t minus t. So the result is e to the power minus st into integration 0 to infinity delta t minus t dt. This area is also unity, so you can write it down e to the power minus st. Moving on to the exponential function, e to the power minus at, that is exponentially decaying curve. Laplace transform of an exponential function is given by L of e to the power minus at, that is equal to integration 0 to infinity e to the power minus st multiplied by e to the power minus at dt. Integration 0 to infinity e to the power minus s plus a multiplied by t into dt. So the integration of e to the power minus s plus a multiplied by t is this by minus s plus a under the limit 0 to infinity. If we put t equal to infinity here, it will be 0, and for t equal to 0, e to the power 0 is 1, equal to 1 by s plus a. For example, Laplace transform of e to the power 3t, it will be 1 by s minus 3. Moving on to the next forcing function, sinusoidal or cosinusoidal function. So let us come to the sinusoidal function. For any voltage v equal to vm sin omega t, let us calculate its Laplace transform. So Laplace transform of Vm sin omega t is equal to, Vm is constant, it can be taken outside the Laplace transform. So Vm multiplied by Laplace of sin omega t. Now Laplace of sin omega t can be obtained from the definition integral 0 to infinity e to the power minus st times of sin omega t. Now from the Euler's formula we have sin omega t equal to 1 by 2j times of e to the power j omega t minus e to the power minus j omega t. So from that 1 by twice j is taken outside the integral, integration 0 to infinity e to the power minus of s minus j omega multiplied by t minus e to the power minus of s plus j omega multiplied by t. So 1 by 2j, integration of the first term gives us 1 by s minus j omega. The second term 1 by s plus j omega. You can verify it by yourself under the limit 0 to infinity. LCM is s square plus omega square, since j square equal to minus 1, and the numerator is twice j omega. So twice j will be cancelled out. So the answer is simply omega by s square plus omega square. So Laplace transform of Vm sin omega t is given by Vm into omega by s square plus omega square. Similarly, for cosinusoidal function also, Laplace of Vm cosine omega t is given by Vm times of Laplace of cosine omega t. Now Laplace of cosine omega t can be obtained from the relation Laplace of 1 by omega ddt of sin omega t. Instead of cosine omega t, we can write it down in terms of sin omega t, ddt of sin omega t into 1 by omega. And we know the rule, if LFT equal to Fs, if we know the Laplace transform of Ft, so Laplace transform of f dash t, that is the first order derivative of function Ft, will be s times of Fs minus f0 plus. So applying this rule, we can calculate the Laplace transform of cosine omega t, which is 1 by omega times of s times of Fs. Fs is what? Because we know Laplace transform of sin omega t is given by omega by s square plus omega square. So s times of omega by s square plus omega square minus f0, that is the ft is sin omega t, so at t equal to 0 it will be 0. So the answer is simple, s by s square plus omega square. So Laplace transform of Vm cosine omega t is given by Vm times of s by s square plus omega square. Moving on to the ramp function, which is denoted by t times of ut. It is a straight line with slope unity, that is tan theta equal to unity. So from the definition we have Laplace of only t. Look, when we are taking Laplace transform of any function, it always started from t equal to 0 to infinity. So no need to write down ut several times. Okay, so t equal to 0 is always the initial condition while we are taking Laplace transform, except the given function is time shifted. So Laplace transform of t can be written as integration 0 to infinity t times of e to the power minus st dt. Suppose t is the u and this is our v. We have integration of e to the power minus st is e to the power minus st by minus s under the limit 0 to infinity minus integration of derivative of u, that is unity 1, multiplied by integration of v dt, that is again e to the power minus st by minus s. So it will be plus into dt under the limit 0 to infinity. So if you compute the first term, it will be 0, since e to the power minus infinity is 0, minus if we put 0, t will be 0, so the entire term will be 0, plus 1 upon s times of integration 0 to infinity e to the power minus st dt. So 1 by s times of e to the power minus st by minus s under the limit 0 to infinity. So this value, if we compute this value, it is also 1 by s. So Laplace transform of t is 1 upon s square. Moving on to the parabolic function given by t square times of ut. Laplace transform of t square is given by integration 0 to infinity e to the power minus st into t square dt. Now t square can be written as integration 2 times of t dt. As we know, integration t dt is equal to t square by 2. So 2 integration dt equal to only t square. 2 is taken outside the integral e to the power minus st into integration t dt. As we know, Laplace transform of a given function ft is suppose given by capital F of s, then Laplace transform integral of that function is given by 1 by s times of fs plus 1 by s times of integration ft dt, which is computed at t equal to 0. Here also we know the value Laplace transform of t is 1 upon s square. So it will be twice of, so fs is 1 by s square here. So 1 by s times of fs is 1 by s square plus 1 by s integration ft dt. Integration ft dt is t square by 2 at t equal to 0, which is coming out to be 0. So finally we can write it down, it is 2 by s cube. Moving on to the Laplace transform of t to the power n. So by definition we have integration 0 to infinity e to the power minus st multiplied by t to the power n into dt. That is e to the power minus st by minus s under the limit 0 to infinity. Derivative of t to the power n is n times of t to the power n minus 1 into integration of e to the power minus st, which is same, minus of e to the power minus st by s into dt. The first term will be 0. The second term will be positive, minus minus will be plus. So n by s is taken outside the integral, integration 0 to infinity e to the power minus st times of t to the power n minus 1 dt, which can be written in this form, n by s times of Laplace transform of t to the power n minus 1. Similarly, repeating the process, we can have Laplace of t to the power n equal to n by s times of Laplace of t to the power n minus 1, which is equal to n minus 1 by s of Laplace of t to the power n minus 2, and so on. And finally n reduces, so n into n minus 1 into n minus 2 into 3, 2, 1, it will be factorial n, and there are n number of terms, so n number of s's are there, so s to the power n. And finally Laplace of t to the power 0, that is Laplace of unity, is also 1 upon s. So this is 1 upon s. So Laplace of t to the power n is coming out to be factorial n by s to the power n plus 1. Next, multiplication of a function with e to the power minus t, exponential of minus t. As we know, if Laplace transform of a function ft is given by capital F of s, then Laplace transform of the same function if multiplied by e to the power minus at, it will be e to the power minus s plus a multiplied by t into ft dt. So it can be written simply as f of s plus a. So this is the property. If Laplace transform of ft is fs, then Laplace transform of e to the power minus at multiplied by ft is given by f of s plus a. For hyperbolic function, sin h beta t can be written as e to the power beta t minus e to the power minus beta t by 2, and cosine h beta t can be written as e to the power beta t plus e to the power minus beta t by 2. So Laplace transform of sin h beta t is integral 0 to infinity half of e to the power minus st multiplied by sin h beta t. So it can be written as s minus beta t minus e to the power minus s plus beta t multiplied by dt, which gives us half of 1 by s minus beta minus 1 by s plus beta. If you compute the integral, you will find this. So this is the answer. Similarly, if you calculate the Laplace transform of this one, cosine h beta t, it will be half of integration 0 to infinity e to the power minus of s minus beta t plus e to the power minus of s plus beta t. So it will be half of 1 by s minus beta plus 1 by s plus beta, which is coming out to be s by s square minus beta square. So let us summarize all the formula of Laplace transform. This is the definition of Laplace transform, and using this definition we have derived the Laplace transform of unit step, which is 1 upon s. Laplace transform of an impulse function is unity. Laplace transform of exponentially decaying function e to the power minus alpha t is 1 upon s plus alpha. Sinusoidal function with frequency omega, sin omega t, omega by s square plus omega square, cosine omega t, s by s square plus omega square. Ramp function, parabolic function, t to the power n function are given by 1 upon s square, 2 by s cube, factorial n by s to the power n plus 1 respectively. Hyperbolic function sin h beta t, beta by s square minus beta square, cosine h beta t, s by s square minus beta square. Now if the functions are multiplied by e to the power minus alpha t by the property, the Laplace transform will be function of s plus alpha. So instead of s, we will write here s plus alpha. So sin omega t is actually omega by s square plus omega square. When it is multiplied by e to the power minus alpha t, it will be omega by s plus alpha whole square plus omega square. This is the Laplace transform of cosine omega t. When it is multiplied by e to the power minus alpha t, it will be, in place of s, we have to write s plus alpha. For time shifted unit step, e to the power minus st has to be multiplied, because Laplace transform of ut is 1 upon s, and if it is time shifted by an amount capital T, e to the power minus st, this factor has to be multiplied. Same for the time shifted impulse function also, delta t minus capital T. Laplace transform of delta t is unity, but when it is time shifted, the same unity is multiplied by this factor e to the power minus st. So in the next session, we will meet again for studying few properties and numericals of Laplace transform. Thank you.